3I Atlas should be a quiet, cooling comet right now at 186 million miles from Earth. Yet the sharpest new images reveal impossible laser-straight twin tails and a density far beyond what physics predicts. The anti-tail alone is 1 million times denser than the solar wind according to Avilobe's calculations, a concentration that no standard comet process can explain. At 186 million miles from Earth, sunlight falls weak and thin, just 300 watts per square meter, a fraction of what reaches our planet. This is the deep outbound track of 3I Atlas, an interstellar comet now drifting through the cold outer reaches of the solar system. At this distance, comets are supposed to be winding down. The heat that once drove furious jets and streaming tails should be fading. Most comets, after rounding the sun, slip into quiet. Their activity drops, their brightness wanes, and their tails shrink as the sun's energy falls off fast with distance. But 3I Atlas did not follow the script. Even before it neared the sun, telescopes caught it acting up. In May and June 2025, NASA's test satellite recorded the comet already active at 6.4 astronomical units from the sun, nearly 600 million miles out, where solar energy is just a trickle. Standard comet models say water ice cannot sublimate at such distances. It is simply too cold. Yet 3I Atlas was already brightening, already shedding material into space. That early outburst hinted at a deeper puzzle. The energy environment was wrong for such behavior. Instead of waiting for the sun's heat to trigger activity, 3I Atlas was firing up in the darkness far beyond the orbit of Jupiter. The implication is that something other than water ice must be fueling its activity. This hypothesis suggests carbon dioxide or even more exotic ices that can vaporize at much lower temperatures, though this remains unconfirmed. As the comet drew closer, the solar power it received jumped from less than 20 watts per square meter at 6.4 astronomical units up to 300 watts per square meter at its current position. Still, that is only about a quarter of the energy Earth receives. For most comets, this would mean a gentle fade, a return to quiet. But 3I Atlas kept defying expectations. The comet's persistent energy, its refusal to quiet down, became the first sign that conventional comet physics might not be enough. Avi Loeb, a Harvard astrophysicist known for his work on interstellar objects, began analyzing the numbers. He focused on the mismatch between the solar energy available and the comet's stubborn activity. The comet was supposed to be calming down. Instead, it was ramping up, setting the stage for the next surprise. Images would reveal a geometry and structure never seen before in a natural comet. November 22nd brought the sharpest look yet at 3I Atlas. Through a half-meter telescope, astronomers captured a bright compact coma flanked by two narrow tails. One stretched away from the sun for nearly 3 million miles. The other, the anti-tail, reached 600,000 miles back toward the sun itself. These measurements held steady in a follow-up image on November 24th, even under poor sky conditions. Multiple observatories confirm the same geometry, eliminating the possibility of camera tricks or processing errors. The tails themselves defy expectations. In most comets, tail material spreads out, diffusing into broad, wispy fans as dust and gas are battered by the solar wind and radiation. But 3I Atlas's tails remain astonishingly tight and sharply defined, their structure holding together over millions of miles. This laser-like collimation stands in stark contrast to the fuzzy, turbulent plumes seen from typical cometary outgassing. The effect is so pronounced that even amateur astronomers using far smaller telescopes reported the same needle-straight symmetry. The geometry presents a persistent 5-to-1 ratio. The away from the sun tail is 5 times longer than the anti-tail, a relationship that has not wavered across repeated observations. The anti-tail's direction is especially puzzling. To maintain a stream of dust and gas pointing toward the sun, the material must be dense enough to push back against the constant pressure of the solar wind. Here, Loeb's estimate comes into play. He calculated that the anti-tail's density must be about 1,000,000 times greater than the surrounding solar wind. No standard comet process can explain such a concentrated, sustained flow. Normally, as the solar wind rams into ejected cometary material, it disperses and thins out rapidly. Yet, in 3I Atlas, the anti-tail holds its form as if locked in place by a force far stronger than simple outgassing can provide. This is not just a visual oddity. The numbers force a direct confrontation with comet physics. Sustaining a 600,000-mile anti-tail at this density requires an engine that standard models do not supply. The result is a paradox, one that can be measured, not just seen. For 3I Atlas, the tails are more than a spectacle. They are a numeric challenge to everything astronomers thought they understood about how comets lose mass and shape their surroundings. Loeb's calculation starts with the numbers. To keep 3I Atlas as bright and active as observed, the comet must be losing material at a staggering rate, about 200 tons every second. Over the 2 months since perihelion, that adds up to billions of tons, roughly 1/10 of the comet's estimated total mass of 33 billion tons. The expectation is straightforward. At that pace, the comet's nucleus should be shrinking fast or even breaking apart under its own mass loss. But that is not what the images show. NASA's Mars Reconnaissance Orbiter captured 3I Atlas as a glowing sphere. Its coma stretched nearly 932 miles across. Inside that cloud, the solid nucleus is tiny by comparison, just a few miles wide, with a total surface area of only 30 to 40 square miles. Yet Loeb's math says that to sustain the observed outgassing, the comet would need about 620 square miles of actively sublimating ice. That is a gap of more than 15 times between what is needed and what is physically available. This is not a subtle mismatch. The numbers point to a crisis. The visible surface area simply cannot account for the mass being lost. Standard comet models would predict the nucleus to fragment, exposing new surfaces and creating a swarm of debris. But even high-resolution images from November 11th show a single intact nucleus. No obvious fragments, no spreading debris cloud. The comet's coma remains smooth and bright, not ragged or chaotic as would be expected if it were breaking apart. The contradiction is stark. The comet is losing mass at a rate that should be catastrophic, yet it shows none of the signs of physical self-destruction. The surface area deficit remains unresolved, raising fundamental questions about how 3I Atlas is managing to drain so much mass without tearing itself to pieces. Spectroscopic data collected by the James Webb Space Telescope and Hubble in mid-2025 forced astronomers to confront an unexpected chemical fingerprint. The gas streaming from 3I Atlas was not just rich in the usual suspects, cyanide, CO2, and water vapor. It carried a strikingly high ratio of nickel to iron, far exceeding what has been measured in any known comet. This included even the previous interstellar traveler, 2I Borisov. In fact, the nickel-to-cyanide ratio was so extreme that it sits well outside the range of solar system comets. The hypothesis that this resembles proportions seen in industrial nickel alloys remains unconfirmed, but the odds of this happening by chance, according to some estimates, are less than 1%. Polarimetric measurements added another layer of strangeness. When astronomers analyzed how sunlight scattered off the comet's coma, they found a level of negative polarization at small phase angles that is more intense than any comet on record. This signature is reminiscent of trans-Neptunian objects, icy bodies from the far edge of the solar system. This hypothesis implies a mix of dark and icy grains unlike what is typically observed, though this interpretation is not confirmed. Mainstream comet scientists acknowledge these values are unusual. They argue that interstellar visitors should be expected to surprise us. With only 2 previous interstellar comets to compare, the sample size is simply too small to define what is truly abnormal. The debate will not remain theoretical for long. On March 16, 2026, 3I Atlas will sweep past Jupiter at a calculated distance of 53,445,000 kilometers. This distance almost exactly matches the planet's Hill radius, the region where Jupiter's gravity dominates. This encounter is being hailed as a natural experiment. If the comet's trajectory or activity changes in ways that standard physics cannot explain, or if its chemical emissions shift dramatically, the data will provide a decisive test. For now, the clock is ticking. Both sides are watching closely, waiting for Jupiter to weigh in. The comet continues its journey through the outer solar system, maintaining its impossible anti-tail and its laser-straight geometry. Each observation adds more data points to the puzzle. The 200 tons per second mass loss continues without the expected fragmentation. The 5-to-1 tail ratio persists across multiple imaging sessions. The million-fold density difference between the anti-tail and solar wind remains unexplained by conventional physics. The surface area problem grows more acute with each calculation. Where standard models demand 620 square miles of active sublimation surface, the nucleus provides at most 40 square miles. This 15-fold deficit cannot be reconciled with current comet theory. The chemical anomalies compound the mystery. The extreme nickel to iron ratio places 3I Atlas outside the known distribution of solar system comets. The negative polarization signature suggests a composition more similar to distant trans-Neptunian objects than typical comets. These are not minor deviations from expected behavior. Each anomaly represents a fundamental challenge to established models. The anti-tail's density alone requires rethinking how cometary material can resist solar wind pressure. The early activation at 6.4 astronomical units suggests volatile compositions far more exotic than typical water ice. At that distance, with less than 20 watts per square meter of solar energy, standard sublimation processes should be essentially frozen. Yet 3I Atlas was already brightening, already ejecting material into space. This activity in the cold darkness beyond Jupiter's orbit points to an internal energy source or chemistry that current models do not account for. The persistence of activity as the comet moves outward adds another layer to the puzzle. Now, at 186 million miles from Earth, receiving only 300 watts per square meter, 3I Atlas should be entering dormancy. Instead, it maintains its spectacular twin-tail display. The geometry itself presents unique challenges. The needle-straight tails, maintaining their columnation over millions of miles, suggest a level of structural coherence unknown in typical cometary emissions. This laser-like precision persists observation after observation. Amateur astronomers using modest equipment report the same striking symmetry. Professional observatories with advanced imaging systems confirm identical measurements. The November 22nd and November 24th observations, despite different viewing conditions, showed no variation in the fundamental geometry. This consistency rules out instrumental artifacts or processing errors. Multiple independent observers, using different equipment at different times, all see the same impossible structure. The 5-to-1 ratio between the main tail and anti-tail remains locked in place. The Mars Reconnaissance Orbiter's images add crucial scale to the mystery. The 932-mile-wide coma dwarfs the tiny nucleus at its center. Yet somehow, this small core generates enough material to maintain the observed activity levels. The math simply does not work. 200 tons per second flowing from a surface area too small to support such loss. 1/10 of the total mass already gone in just 2 months, yet no fragmentation, no debris field, no signs of structural failure. Standard comet physics predicts catastrophic breakdown under these conditions. The nucleus should be splitting apart, exposing fresh ice surfaces, creating the additional area needed for such massive sublimation. But 3I Atlas remains intact. The spectroscopic surprises from JWST and Hubble deepen the puzzle further. The extreme nickel to cyanide ratio stands apart from both solar system comets and the previous interstellar visitor 2I Borisov. This chemical signature has no natural explanation in current models. The polarimetric data tells a similar story. The intense negative polarization at small phase angles exceeds anything in the comet database. This optical property suggests a surface composition fundamentally different from known comets. These measurements are not ambiguous. The spectroscopic and polarimetric signatures are clear, repeatable, and far outside normal ranges. They point to a composition and structure unlike anything in the solar system's comet population. The upcoming Jupiter encounter on March 16, 2026, promises to be decisive. At 445,000 kilometers, 3I Atlas will pass through the giant planet's gravitational sphere of influence. Any anomalous response to Jupiter's gravity will be immediately apparent. If the comet's trajectory deviates from gravitational predictions, if its activity surges or drops in unexpected ways, if its chemical emissions shift dramatically, these changes will provide hard data on its true nature. The scientific community is divided. Some maintain that interstellar objects should be expected to surprise us, that our sample size of 2 previous visitors is too small to define normal. Others point to the accumulating anomalies as evidence of something fundamentally different. The numbers tell their own story. 1 million times denser anti-tail than solar wind. 15 times more sublimation than available surface area. Less than 1% probability of the observed nickel ratios occurring naturally. 5-to-1 tail ratio maintaining perfect stability. These are not subjective interpretations. They are measured quantities that directly contradict established comet physics. Each observation adds weight to the conclusion that 3I Atlas operates by different rules. The persistent activity in the cold outer solar system, the impossible tail geometry, the surface area paradox, the chemical anomalies, the polarimetric signatures all point in the same direction. This object does not behave like any known comet. As 3I Atlas continues its outbound journey, astronomers worldwide maintain their vigil. Each new image, each spectroscopic measurement, each data point adds to the growing catalogue of anomalies. The comet that should be quieting down continues its spectacular display. The anti-tail maintains its impossible density, pushing back against the solar wind with a force no outgassing model can explain. The twin tails hold their laser-straight alignment across millions of miles. The nucleus continues shedding 200 tons per second from a surface too small to support such loss. Right now, 3I Atlas defies every natural explanation astronomers can offer. As new data pours in, each unanswered question pushes the limits of what we call normal in our universe. Sometimes, the rules we trust most are the ones most urgently in need of rewriting.